Imagine leaning into a locked door with everything you've got. Legs braced, arms straight, sweat forming on your forehead. The door doesn't move a millimeter. You feel like you're working incredibly hard, and biologically, you are. But in the physics sense, you've done exactly zero work. That gap between effort and physics is what topic 1.7.2, work, is going to untangle. You already know energy doesn't disappear. It shifts between stores. A falling ball loses height and gains speed, moving energy from a gravitational store into a kinetic one. Whatever the transfer, we measure it in the same unit, the joule, J. Keep that close, because work is really just the rule for counting how many joules move from one store to another. Picture two identical shoves. You push a trolley on a smooth floor, and it glides 4 meters forward. You push just as hard against a brick wall, and it moves 0 meters. Same force, wildly different outcome. That difference in movement is going to decide whether energy actually transferred. So, which push counts as doing work? The trolley, the wall, or both? Take a moment and commit to a reason before reading on. Only the trolley case counts, because the force actually causes movement in the direction it's pushing. No movement in that direction, no work, however much effort it costs you. That case builds our model. Mechanical work is not effort or fatigue. It's the process by which a force transfers energy by moving its point of application. If that point doesn't move, there's no channel for energy to flow through. If it does move, energy flows exactly along that path. Think of it as a pipeline. A force acts. That force causes a displacement, and the displacement is the mechanism that shifts energy from one store into another. Pushing the trolley converts chemical energy in your muscles into kinetic energy in the trolley, precisely because your force acted over that 4-meter distance. Remove the distance, and the pipeline is blocked, no matter the force. We write that pipeline as an equation. W equals F times D. W is work done, in joules, J. F is the applied force, in newtons, N. And D is the distance moved in the direction of that force, in meters, M. Notice the equation multiplies force only by the distance the force actually acts through, not just any distance the object happens to travel. Now connect that equation to the energy idea. W equals Fd, and that quantity also equals delta E, the change in energy transferred. Work and energy transfer aren't two separate ideas sitting side by side. They're the same number, seen from two angles. Every joule of work done is, without exception, 1 joule of energy moved between stores. When reading a force and displacement diagram, don't measure any length that looks convenient. Find the arrow representing the applied force, then measure only the displacement running parallel to it. That parallel length is your D in W equals Fd. Any displacement at an angle to the force must be broken down first, because only the component along the force's direction contributes to the work done. Here's a tempting but false idea. If something moves while a force acts on it, that force must be doing work. Test it with a bag carried at constant height while walking on flat ground. Gravity pulls straight down on the bag throughout, yet the bag moves only horizontally. Because the weight force is perpendicular to the direction of travel, gravity does zero work on the bag, even though the bag is moving and your arms are getting tired. Let's calculate a clean example. You push a crate across a warehouse floor with a steady 20 Newton force, and it slides 5 meters in the direction of your push. Using W equals FD, 20 newtons times 5 meters gives 100 joules of work done. That means exactly 100 joules of energy has transferred into the crate's kinetic energy store. Now, extend the logic to lifting. You hoist a toolbox with a force of 15 newtons straight upward through a height of 2 meters. W equals FD gives 15 newtons times 2 meters, which is 30 joules. Because you're raising the toolbox against gravity, that 30 joules of work becomes 30 joules gained in its gravitational energy store. Your turn. A force of 8 newtons pushes a box 6 meters across a bench. What's the work done? Pause before you check. 8 newtons times 6 meters gives 48 joules. The work done and the energy transferred into the box's motion. Now shift the setting. You pull a loaded sledge across snow with a steady 12 Newton pull, and it travels 10 meters. Work it out yourself before I say the number. 12 newtons times 10 meters gives 120 joules of work done. But unlike the frictionless trolley, that energy doesn't all become motion. Some becomes kinetic energy in the sledge, and some becomes heat from friction with the snow. The equation gives the total transfer. The setup tells you where it ends up. To measure this in a lab, rather than calculate it, attach a Newton meter to whatever you're pulling or pushing and read the force directly. Lay a meter rule along the path of movement and read the distance travelled in the direction of that force. Multiply the two readings together and you have an experimentally measured work done. Newtons times meters, giving joules. Step back and see what ties this lesson together. Whether you're pushing a crate, lifting a toolbox, or pulling a sledge, the same relationship governs every case. W equals FD equals delta E. Work done in joules always equals energy transferred in joules, from a force acting through a displacement in its own direction. Next time you see a force and a movement together, ask one question. Does the force move its point of application in its own direction? If yes, work is done and energy has moved. If no, however hard something strains, physics counts it as nothing at all.